So it's a great pleasure to introduce Craig Huneke at the Fellowship of the Ring, and he's going to talk about linkage and Licci ideals. Thank you, Craig.
Yeah, thank you very much. So before I start, I just want to thank all the organizers for inviting me to talk and giving me the opportunity to talk about something I love to talk about. So given 2 talks on this already, one at SL Math and one in Japan. I hope this will be just enough different so that people who already heard one of those talks really bored. I should say also that in terms of new work, all of this is joint work with Claudia, Polini, and Bernd Ulrich, but I won't get to the new stuff for a while. And finally, I want to point out that I believe I gave a talk in the Fellowship of the Ring seminar in 1980 at Brandeis when it was located. In 2024, unless somebody claims differently, I'm going to claim the biggest between the first and most recent talks in this seminar. David.
I guess I might beat you on that, but you never know.
Well, you haven't given that many talks in your own seminar.
No, but probably give some.
All right, so the topic of today is linkage and Licci ideals. The first part will be an introduction to it. And then the second part is going to be about some conjectures and a dream. And I'll only give a couple proofs, I think, this time. I'm not going to go into great detail about some of the arguments because I want to sort of give more about the scope and the dream of this work rather than all sorts of details. So I wrote most of it. I left some blank pages to do a little math. Mainly because I was afraid I'd forget stuff if I didn't write it. So throughout this talk, SM will denote either a regular local ring or a standard graded polynomial ring with homogeneous maximal ideal M. And in the latter case, the ideals will always be homogeneous when I talk about them. I won't even bother to specify most of them. So the basic definition about linkage I'm using comes from a paper of Peskine and Szpiro. I should say that there's a very long history to linkage, even going back to the 19th century, but I'm not going to talk about that at all. So 2 ideals, I'm just reading, and I hope you can read along with me. 2 ideals, I and J and S, and I'll just remind you they're homogeneous if I'm in the polynomial graded setting, are linked with respect to a regular sequence. Alpha equals alpha 1 through alpha c. And that's denoted with a little squiggly line and the alpha underneath. If alpha colon I is J and alpha colon J is I. So this is the algebraic definition that Peskine and Szpiro gave in the early 70s. There was a lot of work on linkage in that time, and I should mention, even though I'm not going to be talking about the Hartshorne-Rao module, Hartshorne had a big impact with his student Rao, and that's classifying various linkage classes in the graded case. So let me point out right away that this definition forces both I and J to be unmixed of codimension C. That's just because the alphas are a regular sequence, and they're both colon ideal. By the way, please interrupt questions if you have any. I guess maybe Claudia is keeping track of the chat as it goes, or if you have comments also, I would appreciate them. So, in fact, I should point out right away that if one of the ideals, say I, is unmixed, and then you just define J to be alpha colon I, then that should say then, not the, then the opposite colon also holds that I is alpha colon J. So then they're linked through this regular sequence. So using this, you can just start with an unmixed ideal I, take a regular sequence, maximal regular sequence in it, take the colon, and it's linked. And you can continue this way. So it's sort of a dynamic process, and you can give many examples in this way. Another way to think about it, for people who haven't before, is if you take a primary decomposition of just some arbitrary regular sequence alpha, and so the Q1 through Qn are its distinct primary components belonging to distinct primes. And you just split them up in any way you want. So you intersect the first I and call that I, and intersect the last of them and call that J. Then I and J are linked through alpha. It's easy to check. So this maybe is more classically how it was thought about. So I want to give two examples. They're sort of baby examples, but I hope they'll appeal to some people. The first is very well known, but I'm doing it explicitly. So suppose you have an n by n plus 1 matrix with entries in M, such that the n by n minors of A, the maximal minors, have grade 2, which is its maximum grade. Then let me write delta sub I to be the n by n minor of A, given by deleting the ith column. And I don't, they do come with signs, but for what I'm going to say there, those signs are irrelevant. And just assume that the last two of them form a regular sequence. You can always, I mean, it's grade 2, so you can certainly rearrange the matrix so that that's true. Then define B here. Maybe I should circle it or something. So B is this guy right here. That's an n minus 1, first n minus 1 columns of A. And then I peeled off the last two columns. And you might note, just in the way of passing, that the delta n and delta n plus 1 are in the maximal minors of the matrix B just by the Kramer expansion. So then it turns out that the link of I n sub A with respect to this regular sequence is exactly the n minus 1 size minors of B. And notice when you do this, so I've written down here that there's no A prime there. That should just be A. So this links these n by n minors, which have n plus 1 generators, to the n minus 1 size minors, which have n generators. So you've decreased the number of generators to it. And you can just repeat this. And by repeating it, you can, of course, decrease until you can't go any further. And you decrease the number of generators by 1 each time. So eventually you reach a regular sequence. And this is a very special property of codimension of these minors. And such ideals that you can eventually get to a regular sequence are called Licci. That stands for linkage class of a complete intersection. That's where that word comes from. And that's going to be the main topic of this talk, or Licci ideas. But I want to give another example of linkage, which might appeal to people who work on monomials. And monomials are going to come up a lot in this paper, in this work. So if I is a square-free monomial ideal, then I write its primary, it's an intersection of primes. Each of the primes is just a set of the variables, some generated by a subset of the variables. Then I can define I check, which is called the Alexander dual, by taking the monomials MP sub 1 through MP sub L, where if P is generated by a bunch of the variables, then the corresponding monomial is just the product of those variables. So this is one way to define the Alexander dual. And of course, as probably almost everybody who's listening knows, and especially those who work on Stanley-Reasoner rings and monomials, there's strong duality properties between these two. And one way to see that is through linkage, as it turns out. If you add in the squares of the variables to I, and then link with respect to those squares of the variables you actually always get the Alexander dual plus the squares. So, linkage has a lot to do with duality. This is just one avatar. And I always use this as a fast way to compute the dual, but I'm sure Macaulay has better ways to do it. So I'm actually going to start this right away with a conjecture that Claudia and Bernd and I made. And I want to put it out there right away. I'm actually going to make 4 conjectures, but this is the first one. So it just says, if you have a square-free monomial Licci ideal, then the Riesz ring is Cohen-Macaulay. Now, for people who study Riesz rings, this is a very strong property. Say a Riesz ring is Cohen-Macaulay. And the only condition is square-free and Licci. And where this whole thing started was when we were listening to a talk of Liana Shega. And in that talk, the authors of the paper listed below it, they actually proved this in height 2. I mean, it's not the main point of the paper, but along the way, they prove this. And they prove it for height 2 ideals, which are square-free and Cohen-Macaulay. But of course, the height 2 Cohen-Macaulay ideals are, by the Hilbert-Birch theorem, given by maximal minors of a n by n plus 1 matrix. So we know they're Licci already by the first example. Basically, whenever anybody proves anything about a height 2 Cohen-Macaulay ideal or a height 3 Gorenstein, I immediately think Licci. I think it must be true in general. I also want to mention concerning this conjecture right away, before I forget, is that Tarai in several papers with various co-authors, there are subsets of them in every paper, Kimura, Yoshida, Inye, and Rinaldo, classified square-free monomial Licci ideals actually in various cases. For instance, 4-dimensional, those generated in degree 2, and some others. And when we first thought this conjecture might be true, we checked all of them, and they are true for all these classified examples. There are many of them. I may show 1 or 2 because I might want to illustrate another point later on. But right now I want to move on.
Greg, I would like to say there is a question on the chat, but I think you just answered it. And the question was from Jonathan Montagno that asked, do you have more evidence besides the H2 case? And now you just told him that you have much more evidence besides the H2 case.
There's much more evidence coming.
Yes.
But I like getting the problem out right away. Did that answer the chat well enough?
I think so. In fact, he said thank you.
Craig,
Yes.
is the Licci property reflected by topological properties of a corresponding simplicial complex in the square-free monomial case?
So that, I think, is a question I don't know the answer to, but it's going to come up in the dream.
Okay.
I have a dream.
Then does that mean we can't go to sleep or that we can?
It means this talk will put you to sleep. So I want to, as I said, I'm going to discuss generalizations and results concerning that conjecture, but in the second half of the talk, I want to sort of continue with a general introduction for a while. So I could have waited to say the conjecture, but in some sense I want to put it out there right away. Well, I did want to put it out there. So why are Licci ideals interesting? I mean, they may not be. I have to say, this is a very exciting time in this study because a lot of things came up in the SL math program that was just held last spring. And there are lots of questions, and I think there's a lot of chance for progress where there didn't look like there would be for a long time. So why are they interesting? Well, this is sort of putting the cart before the horse. But even the fact you can make a conjecture like conjecture 1 tells you something must be interesting. I mean, they must have strong properties. So 2 of the main properties that were proved in the I guess in the 80s, where first the thesis, the habilitation of Boukweit's in Paris, he proved that if I is Licci, then the so-called twisted conormal module, I mod I squared tensor, the canonical module, S mod I, is actually Cohen-Macaulay always. This is very strong. It's so-called strongly non-obstructive. And not too long after that, it was proved that if the causal homology modules of I are also all Cohen-Macaulay, and this was dubbed strongly Cohen-Macaulay. So this means you take any set of generators and you compute the causal complex and look at the homology. And those turn out to be all Cohen-Macaulay modules over the maximal Cohen-Macaulay modules, in fact, over S mod I. So they all have the same dimension. Of course, the very first one, H0, is S mod I. So in particular, Licci ideals always define Cohen-Macaulay quotients, and that was known for a long time. In this context, Peskine and Szpiro deserve credit. And I put a little parenthetical mark about structure theorems because that was more to remind me. In some sense, this strongly non-obstructed condition means that you can always deform a Licci ideal to some kind of rigid object, which is a specialization. And in some sense, that rigid object is a structure theorem for that particular data. And good examples are the Hilbert-Birch theorem in codimension 2, or as we'll see in a moment, the Buchsbaum-Eisenbach structure theorem.
Greg, there is another question. Sorry to interrupt.
Okay.
The question says, the question is, has anyone studied if the Licci ideal are invariant under the action of monoid and inclusion and symmetry group or not?
So, not that I'm aware of. Maybe Bernd or you are aware, or Robin, some of the experts, but I don't think I'm aware of.
Me neither. Bernd, are you aware of anything?
Not really, no.
Me neither. Paolo, do you know? No. Okay. So we can go on. Sorry, Craig.
Oh, I like questions. I love them. And I'm really not in a rush. I can cut some of the end if it goes too. So for those who've never studied linkage, I want to point out the resolutions can be computed. So I here is Licci. S, remember, is a regular local ring or a polynomial ring. So you have a finite free minimal resolution, and the length is the codimension, the height of I. So I wrote it up there, FC to ... F1 to S mod I. And I'm taking a regular sequence alpha inside I. So there's a surjective map from S mod alpha to S mod I. The resolution of S mod the alphas is the causal complex, so exact. And there's induced comparison maps. And Peskine and Szpiro give the resolution of the link, which would be alpha colon I. And remember, that is a link because I is unmixed here, Cohen-Macaulay. And they do it by just dualizing and taking the mapping. So I wrote out the first few terms to show you what it would look like. Now that's usually non-minimal. And in fact, all the action in some sense in trying to understand Licci ideals is in understanding where they're splitting in those comparison maps. It's a very difficult question, and it's what makes it both interesting and hard at the same time. So that's how you get the free resolution. Remember, I'm always in the regular case here. By the way, almost all of this goes through in the Gorenstein setting, but and I don't want to mention there's a vast amount of work in the Gorenstein setting or with Gorenstein linkage, and I'm just not going to talk about it for this talk. I don't have time. So I want to do some more introduction here, because in codimension 3, there's been a lot of really amazing stuff lately to me. So I first want to point out what I already said. Every codimension 3 Gorenstein is Licci. And you can use the Buchsbaum-Eisenbud structure theorems to prove this, but the first proof actually was by Junzo Watanabe, 1972. He proved that every Gorenstein had an odd number of generators, but the way he did it was by basically showing that you can go from a 2n plus 1 generated one and double link it to a 2n minus 1 generator. So in that way, he showed that you could get down to a complete intersection eventually. Next, I wanted to mention what I think is really spectacular work of Guerreri, Ni, and Wayman, who have been studying the structure of resolutions of link 3. And they form these generic rings, and they're not Noetherian very often, but they're basically exactly Noetherian in the Licci case. And one side consequence of their work is what I highlighted in red on the page you're looking at. If S mod I is Cohen-Macaulay and codimension is 3, and either the deviation of I is at most 2, the deviation is the number of generators of I, which I'm calling mu of I, minus the codimension, which is 3. So if either both, I should have said both, the deviation is at most 2 and the type is at most 4, R is the type, or vice versa, then I has to be Licci. And this comes from these structure theorems. I know no way to see this without using their very intricate methods. And in general, they make a pretty amazing conjecture. It shows how special Licci ideals are actually. That if 1 over C minus 1 plus 1 over the deviation plus 1 plus 1 over the type plus 1 is bigger than 1, then ideal has to be Licci. Of course, they're not saying if and only. This should always force Licci. So I learned about this and heard talks at SL Math last spring.
But Craig, I do think they show that it's sharp in the sense that if you go away, at least in the codimension 3, if you go away from this type, then you always find an example that is not Licci.
Ah, I see. Just from that data alone.
Yeah,
Yes.
just from that data alone.
Yes. Okay.
They do show it's sharp. And I do think they prove also the general conjecture. I mean, Ni is here. They prove the general conjecture for C equal 4 as well. That's all, I think. I just talked to them in Krakow. I think they are also for C equal 4.
So let me summarize like I understood. So for codimension 4, they've proved this now?
Yes, I believe so. I mean, Ni is here, but I believe so, yes.
And it's sharp in the sense that if you fix C, delta, and R, and this isn't true, there will be some example that's not.
Exactly, yes. Now it says, unfortunately not, but hopefully soon. So I don't still have it, the C equal 4.
Oh, okay.
But I do have the sharpness.
Wow, very good. All right. Thank you. All right, another work I just learned about at SL Math, which I want to mention, is it's just out on archive now, and it's the following theorem of, I'm really sorry, I cannot pronounce correctly that first name. I'll just massacre it if I try. And Ram Kumar and Samartano. And I'm just going to state their theorem here. They prove a lot more, but this is one of the main points. So they have an ideal in, so this is going to be a codimension 3, ideal of colength D in 3 variables, and it's monomial. And they prove the following are equivalent. First, that when you think of it as a point in the Hilbert scheme, so the colength is D. It's smooth. And second, the ideal is actually Licci. So again, this shows you, in a sense, how special Licci ideals are, but they're sort of right on the border of many problems, I think. And they actually conjecture, so this, monomial ideals are always on the smoothable component. So they also conjecture that exactly the same equivalence holds if S mod I, the point S mod I lies on the smoothable component of the Hilbert scheme. And that's a great problem. As far as I know, it's wide open. They do show how one might approach it, but I don't want to go into that. So I want to now get to the dream conjectures. So I've taken about 30 minutes. I think this talk will probably be about an hour. Would that be okay without a break? Or I can't. I hear you, Claudia. It's good. Okay.
It's good.
Yeah.
It's good.
Yeah, that's
It's
good. That's good.
Okay. I didn't try to make it too long. So the dream and the conjectures, and all the results now are basically anything I prove are joint with Claudia, Polini, and Bernd. So here's the dream. And maybe it's just my dream. I don't want to claim it's Claudia or Bernd's dream. So take an ideal, as always, in this case homogeneous though, and look at its Betti table, which you can display with the usual diagram or not. So I've defined the Betti number, the graded Betti numbers there for you. Then the dream is to prove there exists an algorithm based solely on this table and the codimension, because you got to check its Cohen-Macaulay, giving necessary and sufficient conditions for I to be Licci. So by algorithm, I mean, you might have to maneuver some with the Betti numbers, but it ought to be a finite process from those Betti numbers to determine if it's Licci or not. And I'm going to give you a lot of evidence why this has a chance, and then I'm going to show you why it doesn't have a chance at the end. But there's no counterexample. And Mel, this is sort of relates to your question, I think, about the topological, like in the monomial case. Those Betti numbers, as you proved, were topological invariants. So in theory, maybe there is. And
So
I got,
Craig, does this just say that the Betti numbers determine whether it's Licci?
yes, yes.
That's a
That would be
equivalent.
a simpler way to say it, but I sort of want to emphasize you might have to do it through a process that's not, you can't just look at it necessarily. Yes.
Well,
But yes, I'm saying that that Betti table determines whether it's Licci or not. That's the dream.
okay. So if your two ideals have the same
Betti
Betti
table.
table, then they're both Licci or both not Licci.
That's what I'm hoping.
Okay.
Well, same codimension too.
Yeah.
Okay. So you may think that dream is really a nightmare, but at any rate, that's my dream. You can't take it away from me until you give a counterexample. All right. I do want to say it's not going to come in for a while, but there is one necessary condition from the Betti table that's been known for a long time, and it forces others. So let capital T sub I be the largest shift in homological degree I in the resolution, and let little t sub I be the minimal shift in homological degree I. I should mention this is not common. In fact, in some papers, little t sub I is the maximum. I prefer the big T for this particular. So for example, T1 would be the largest degree of a minimal generator, and little t1 would be the smallest degree of a minimal generator. So the main known restriction on the Betti numbers for a Licci ideal, sorry, it's my spam, I'm sure. I'll wait for a second till, I don't know if you can hear my phone ringing. So the main known restriction is that the largest shift at the end, capital T sub C, has to be strictly bigger than C minus 1 times the minimum degree of a generator. And this appears in a paper in the 80s by Ulrich and myself. And I should say right away, it forces similar type restrictions on the T sub I using work of Eisenbud Bernd and myself. And we actually have proved some improvements of this, but I didn't want to get into the weeds too much. But it does show that there are restrictions on the Betti table, for sure. And this is very strong, this particular. Any questions on the dream or the restriction to this point?
Is there any class of ideals for which you can prove it?
Thank you for that question. And yes, sort of. I'm coming to that. I'll tell you both positive and one sort of slightly negative result. So I want to go to conjectures now. I'm going to make 4 conjectures, and this is sort of the order we did them. So I'm going to recall the first conjecture. It just says that if I is square-free monomial in Licci, then the Riesz ring is Cohen-Macaulay. So conjecture 2 says the following. It says something more specific, or sort of unrelated to start with. So suppose you have a square-free monomial, Licci ideal, and a polynomial ring in n variables, then the claim is it can never have more than n generators. So what I want to write out is why conjecture 1 implies conjecture 2. Point that out. So now I'm actually going to write something.
Conjecture 2 implies conjecture
The
1.
other way around.
Did I just say 1 implies 2?
Yeah.
Yeah.
Mhm.
You
It
meant
does.
2 implies 1.
It does. Well, actually, I don't know if it does, but at any rate, conjecture 2 implies conjecture 1. So why is that? Well, it's because old work of Herzog, Simmons, and Vasconcelos. And I think I did this, but later in another way, which says that if I is strongly Cohen-Macaulay, and if you remember, that means that all the Cazul homology modules are Cohen-Macaulay, and the number of generators of I locally is at most the dimension locally, E is in spec R, then the Riesz ring is Cohen-Macaulay. And in fact, it's isomorphic to the symmetric calculus. So this is a theorem of Herzog, Simmons, and Vasconcelos from the 80s. And so the conjecture 2 just says that this condition holds at the maximal ideal. But when you're dealing with monomials, that's everything, because the only relevant primes are where you invert some of the variables, and then it's again a square-free monomial. So applying the conjecture to that case shows you that conjecture 2 implies star. And then we already know Licci's and Licci implies strongly Cohen-Macaulay. And so you just have to apply the theorem of Herzog, Simmons, and Vasconcelos to prove conjecture 1. And again, conjecture 2, we checked on all the Turai examples, and sure enough, it always holds. It's very weird. There's no apparent reason why this should be the case. But let's make some more conjectures. So after some thought, we realized that every time we could prove it, we were proving something much better and getting to a more general situation. Namely, we conjecture the following. If I is homogeneous in Licci, then the number of generators is always bounded by the top shift at the end. So capital T sub C is the top shift at the end. Well, negative of the top shift. But, so let's do conjecture 3 implies conjecture 2. This is even easier. So conjecture 3 has nothing to do with monomial ideals. So when I say it implies conjecture 2, I mean in the monomial case. So by the Taylor resolution, complex, I guess, not a resolution. Well, it is a resolution. It's not minimal. the last shift, multigraded shift, of a monomial idea is, of course, just the product. If you put in the multigrade. And so that n must bound the top shift. In general. You get that top shift by taking LCMs of the generators, basically. So now it's obvious that conjecture 3 implies conjecture 2. Just to go back to what conjecture 2 said for a moment, so you haven't forgotten. It just says that the number of generators is bounded by n. So if the number of generators is bounded by TC, it's certainly bounded by n. That's why conjecture 3 implies conjecture 2. Easy. And again, checking all known examples that we had at that time, conjecture 3 still was, had a chance. Okay, let's go to conjecture 4. Well, I wanted to get out of the Licci, of the homogeneous case. And if you have a homogeneous Licci ideal, you can always, remember it's Cohen-Macaulay, so you can always cut down by linear forms till you reach an imprimary. And in that case, the last twist is related to the Sockle degree. And the Sockle degree, so the last twist, let me just say, well, let me read you the conjecture. So if I is Licci imprimary, and the deviation is delta vi, which is mu of I, the number of generators minus the dimension, then it says that m to the delta of I is not in M. And that's simply because there exists Sockle elements. Well, I should say conjecture 4 implies conjecture 3. Because there exists a Sockle element of, when you cut, a bar just means you cut down to dimension 0 of degree TC minus, minus C, I guess, minus C. And of course, the dimension of S bar is C. No, it's N minus C, I guess. I did something wrong here. Should be the dimension. And so if there's a Sockle element in that degree, then if m to the,
No, it's minus C, minus C.
It is minus C.
Hmm?
Oh, the deviation is a codimension. Oh, the codimension is the, yeah, okay.
Greg, could you say again what S bar and I bar are?
This is S bar is S mod a general system of parameters.
Oh, that sense of cutting to dimension 0. Okay.
Yeah, so the dimension is C. Not, see, I'm just confusing myself here. Yeah. You just cut down. It doesn't change the Betti numbers when you cut down
Yeah.
regular sequence. Yeah, so so the, how do I want to say this? Okay, I'm getting mixed up, so I'm just going to leave it for you as an exercise. So this easily implies. Conjecture 4 implies conjecture 3. Because remember, the conjecture is just mu of I is at most T sub C. That's conjecture 3. So this conjecture 4 is very general, and that can be checked a lot easier. So I want to give you 2 simple cases where I can do the proofs quite easily before I move on to a little bit more. So here's, people were asking me what the evidence is. So here's some of the good news. So in the Hilbert-Birch case, I want to actually give two proofs because one is that, well, in this first case, they're really the same, but in the second case, they aren't. So in the graded case, I'm trying to prove conjecture 3. So I just want to know that mu of I is at most the maximum last twist, which is T2 in this case. But of course, you have the graded resolution here. So there are twists here. There are twists here. But the twists are just the degrees of the generators plus, it's the biggest one where you add generator degree plus column degrees of the presenting matrix phi. But phi has at least linear forms. If you take them, this is a minimal presentation. And we know these are the n by n minors. So this is at least, if they're all linear, you would have generating degree n plus linear. And so T2 has to be at least n plus 1, which is the number of generators. So that's the graded case. Now, the non-graded case, which does imply the graded case, is even easier. So I want to just write it out. Non-graded. So in this case, let's just see what it says. This is minimal again. So it's saying that M primary. So codimension 2 and dimension 2. It just says that M to the deviation should not be enough. Well, the deviation is M to the n minus 1, because n plus 1 minus 2 is n minus 1. So that's M to the deviation. And of course, I is in M to the n, because by the Hilbert-Birch thing. So this is clearly correct. That's a true statement. Well, just a second. Our cat just got stuck in our closets. I think I better let him out. Where you were in there. Sorry about that. So codimension 3, Esmond Gorenstein. So not to belabor the point, in the graded case, this is an easy consequence in the same way as the Hilbert-Birch. Of the Buchsbaum-Eisenbud structure. I won't even go through it. And when I say the graded case, I mean this is conjecture 3 holds. But something interesting already happens in the non-graded case. That's why I wanted to do these separately. I want to see what it says. So we know from the structure theorem that I has, I guess I should just put I here. I'm doing the minimal. So the conjecture 4 says the following. So so what's the deviation? Well, the deviation is 2n plus 1 minus 3. So the conjecture says, and again, I'm assuming M primary for conjecture 4. It just says M to the 2n minus 2 should not be enough. That's the statement. This is the statement. Now, all we can guarantee about I is that it's in M to the n. And this is because they're the Pfaffians. So we know I is M to the n, in M to the n. And we need to show that m to the 2n minus 2 is not an I. And this is non-graded. This is the local situation. So how do you do that? Well, I think there's several ways, but we found the easiest quick proof of this is that Loeffel showed all such ideals in exactly this range, by the way, showed that if I is between these bounds, then S mod I is gold, which I'm not going to define. And for experts, Golod and Gorenstein don't go together. That's a contradiction. So then S mod I is not Gorenstein. And that proves this case. I'm not claiming this is the only proof, but it's the quickest proof. And already the non-graded case, you can see there are issues coming in, and in the graded case really is much easier. So, okay, this is doing all right for what I want. I want to give you, people were asking what the evidence was several times. So I'm going to basically list every case we know that the conjectures hold, and in some cases I'll describe where the dream holds. So here we go. I'll just say a word or two about every one of these, but not much. Each one of these would take almost a whole talk to do carefully. So the first case we can do is if the ideal has a maximal regular sequence of quadrics. This always assuming Licci. And when I say we can do it, I mean all the conjectures hold wherever they apply. And the proof actually shows something much stronger because of work of Chong. It shows that for all such ideals, the Eisenbud-Green-Harris conjecture holds. I don't want to go into what that means, but basically says the Hilbert function is given by the squares of the variables plus a Lex segment ID in this case. Okay, so that's one. Oh, and moreover, in this case, I'm not going to write out, but, well, maybe I will write it. So I'm going to put a little star here. And here's the comment, side comment. If, let me say the codimension is C here. So if all the last Betti numbers are at least 2, and all the first Betti numbers are at least 2. So all the graded Betti, so for instance, you can't have just like one cubic in the idea or something like that. Then the dream holds. In other words, we can give necessary and sufficient conditions for the ideal to be Licci of anything containing a regular sequence of quadrants with these additional conditions. And it's rather technical. It's quite beautiful, I think. I mean, it's like anything. It's really technical until you look at it long enough, and then it looks really beautiful. But I don't want to go into it. But it is evidence that the dream has a chance. Okay, 4, you may have been reading ahead. 4, the conjectures hold for any M primary Licci monomial ideal. And these are not square free, of course, just monomial. This follows because there's an algorithm to determine if a M primary monomial ideal is Licci due to Bernd and myself. And the algorithm is sort of an inductive one, and you can follow along that inductive procedure to prove the conjectures in this case. And for homework for Bernd and Claudia, which I hope they'll do by the time I get down to 8, is this would be a very natural case to prove the dream holds, I think. And you could do it in 2 ways. You could either explicitly say what the Betti numbers have to look like, or because of the algorithm, one might be able to prove that if it's not Licci, it has to have a Betti table that differs in some spot from a Licci. I think this would be a good place to look.
That's a very difficult task to do in just a time.
You guys are smart, you know.
By the way, Greg, 4, as we discussed also last week, remember, but 4 is really true if and only if you have a maximal regular sequence of monomial.
Yes, that is, yeah. So,
Mm.
yeah, I don't, well, let me get into that in a little
Great.
bit. I do have a comment about that. So another case we can do is we can show Licci, this is for the M-primary conjecture 4 case. We can prove that if it's Licci and the deviation is at most 3, the conjecture holds. And this work is, it really uses a lot of things. It analyzes the Hilbert function, and it's quite involved there. Another case we can, and it even goes back to some of the Eisenberg-Green-Harris stuff. So another case we can do is if it's Licci with nearly pure resolution. So by nearly pure, I mean that all the twists in the resolution are the same in every homological degree, except possibly the first syzygies are allowed to have different degrees. So I can write it out formally, but since I'm not going to prove any of this, and this I sort of sketched the proof in the Berkeley talk. So Robin, you probably heard this one. This is,
Maybe.
this uses Boyd-Soderberg and works quite beautifully. Recently, we also realized, and this is sort of, we thought we had it, we lost it, and now we have it back, is every Licci-Gorenstein ideal, which is homogeneous and equigenerated, the conjecture 3 holds. So the graded one is conjecture 3, the non-graded one is conjecture 4. So these are true in these cases. And this again is a finer analysis of Boyd-Soderberg and some work of Herzog and Srinivasan dealing with sort of the convexity of the.
But wait, that requires monomial. So.
Oh, right, you're right. Thank you. Yeah, because we're using Herzog and Srinivasan is only for monomial. Yes, thank you. Okay. I want to say a weird one, which again, I don't want to go through the proofs, but suppose you know the conjecture holds for homogeneous Gorensteins. Then it actually is true for over 50% of homogeneous Cohen-Macaulay, which are generically a complete intersection. So basically, I can describe why. It, if you take a homogeneous Cohen-Macaulay generic complete intersection, you can link it with a complete intersection that generates it generically, and then it moves away the components. So if you link I to J, you can link I to J in such a way that the sum is height C plus 1, not C. And in that case, Bernd showed that I plus J is actually Licci. And we can apply the conjecture to I plus J if it's true for Gorenstein. Oh, and also I plus J is always Gorenstein in this case. So I plus J always turns out to be Gorenstein-Licci. If we assume it's true there, then you can read off the Betti numbers and you can show that either it has to be true for either I or J. And in the case it fails, it's actually quite restricted. That's why I put over 50%. So it's sort of an odd result, but it does sort of focus attention on the Gorenstein case as very crucial. So that, I think, is a list of virtually all the cases where we can actually prove the conjectures, and in one case, more or less prove the dream. So before I go to the next slide, are there any questions about any of this long list of ones we can do?
Yeah, I have a question.
Yes,
Could you could you begin to make a list of all Betti tables corresponding to Licci ideals?
So the problem, of course, you can start with a complete intersection and then link it with some complete intersection inside of it.
Yeah.
You can continue to use the Peskine and Szpiro mapping cone construction, but the trouble is the splittings get in the way. And where they occur and how often they occur mess up the Betti tables. So that's really difficult. Now, I think in case 4, I think we'll either prove it or get a counterexample. So, I mean, prove it in that case. Or there could live a counterexample in that realm, actually. It's conceivable.
I have a question.
Yeah.
In case 3, where you know the dream is true, in the subcase where you know the dream is true, can you formulate the condition on the Betti table in some simple way?
So I didn't write it down and I would get it wrong. It basically only relates to the generators and the last twist. And what it is a series of inequalities on the size of the Betti numbers and the gaps. So the size of the Betti numbers at the end and the gaps between the Betti numbers and the first and the generators. And then by the exact reverse of that also. So when you link, the Betti table sort of reverses because it's a mapping dual. So, and of course, if you link a Licci ideal, it's still Licci. So whatever condition you have has to be symmetric. And our condition is exactly saying that the Betti numbers are sort of bigger than the gaps that come from the generators, the Betti numbers at the end, and then vice versa. It's a beautiful, as I said, it's quite gorgeous, but I better not try to write it down without having my notes. But that's what the condition is. And in fact, you can see it should work in general without the restrictive conditions, but without these restrictive conditions. But the trouble is the splittings start messing you up when you don't have these 2s, and it's gotten very hard to say exactly what the condition is.
Yeah, may I ask a question? Correct.
Of course.
Yeah, it seems if the ideal is directly linked to a complete intersection, then conjecture 3 holds, right?
Yeah, I guess in that case. Yeah.
Yeah. So did you check if number of steps has any role in the validation of the conjectures? Number of steps to get to a complete intersection.
Yeah, that's a great point.
Yeah. Okay.
I think, see, it seems, let me just go back to 3 for example. What we use in 3 basically is this one known, we use this one known restriction, which I'll go all the way back. This one. We use that this restriction has to hold, but the point is it not only has to hold for the ideal, it has to hold for all the links. So as you carry that through linking these quadrics, you get more and more restrictions. And they're very tricky because of the splitting. And the number of steps definitely makes a difference. Yes, absolutely. In fact, in the actual dream, in that case, you have to be careful about where you cut it off, which has to do with the number of links you may require to sort of answer. I mean, I think when Bernd and I first proved that inequality, I was very naive, and I thought maybe that would even force just that one inequality. That was a very, very naive hope at the time, but it really seems more within reach at this point. So let me end.
I mean, the inequality, if one strengthens it, perhaps, reversing the roles of maximum and minimum. That's still open. That's still open. Whether that.
Yeah, if we have
individually sufficient, it will not be an effect.
Right, but at least would be sufficient.
Well, finding sufficient we have now a lot more actually than we did that I didn't mention. But not yet necessary in general. So let me do the pessimism. This is my last slide, I think. I'm gone a little bit over, but I hope that's okay. So I want you to peruse 3 Betti tables. These are in a paper by Migliore, Nagel, Ulrich, and myself. And I want you to tell me the differences in these tables. So, of course, I'm pretty bad about writing out the Betti tables by hand, but I hope you can see that the difference between A and B is simply here and here. That's the difference between those two. Now, what's the difference between B and C? Does anybody see what the difference is? All these have the same Hilbert function. Well, I hope you can't because they're the same.
That's what I was going to say. They look the same to me.
Yeah, these are the same. So in this paper, there are 3 examples. So this one is imprimary monomial. Not Licci. This one is Licci, but not monomial. Well, if the dream were true, this has to be Licci, and it is. But here's the subtlety. For this one, well, it doesn't matter because they're the same, but for one of them, and I'll say B, it's Licci, but not minimally homogeneous Licci. These are obviously homogeneous because I'm writing down. By that I mean you can eventually link it to a complete intersection, but if you use regular sequences of minimal possible degree at every step, you can never get to a complete intersection, ever. Now this one, it is minimally homogeneous. So this one, although it looks exactly the same, you can choose regular sequences of minimal possible degree. And the difference actually is in this one, the 2 quadrics here are height 1. So you can only use one of them in the minimum. Whereas in this case, these are height 2. And if you have to do minimal homogeneous links, you have to use both of them. And you can never get to, if you keep doing it, you can never get out of that. You can never get to leaders. So this is pessimism because it shows you that even though it's true, the dream holds in some sense for these. That is, these 2 are Licci and that one's very close, but not. But you can't just do something obvious to prove it if it's true. So this could easily create some grounds for pessimism that this dream has any chance at all. Finally, I want to mention one of Robin's favorite points is that in all these versions of Licci where you go between local and graded, in the graded case, I was talking about homogeneous links, but you could talk about non-homogeneous links, or you could also just localize at the irrelevant ideal, think about the Licci in that case. And the relationship between those 3 types of being Licci are not totally understood at this point. It's a question of which ones are which. But I think that's it for my slides. So thank you.
Craig, I have one more question.
Sure.
Which you won't like, but I have to mention it sometime during this talk. And that is, the whole talk seems to be about the relationship, the behavior of resolutions and Betti numbers under linkage. So
Yes.
what happens if you use Gorenstein linkage instead of complete intersection linkage?
Yeah. Well, that's too hard for me, I can tell you that. I mean, I guess you can do similar. I mean, if everything's perfect, then I suppose there's comparison maps. But I really This is
I mean,
already, this is
yeah.
too hard for me already. Of course,
the
the
mapping construction still works, but of course.
you could do it. But also, the, Gorenstein linkage doesn't preserve the same properties of strongly non-obstructed, strongly cone-Macaulay, which have always been, for me, one of the reasons these Licci ideals are so interesting. But they are special because of that. Gorenstein linkage is much special.
Also, you have the same problem that you have always with Gorenstein linkage, because if you want to try to produce all the Betti table, you have to be able to, you start in the case of Licci, you start with the regular sequence. The Koszul complex is the resolution. And, so we have it once we have the codimension. But for Gorenstein, there could be, who knows what we don't know all the Gorensteins. And that's really the problem. So you could really get, it could be that every perfect is Licci, because it could be that you could produce any possible Betti table. I mean, we don't know. It's the same problem.
Yeah, I guess my point is maybe these counting techniques or quantitative techniques might help work on the problem of something that's glitchy, but something that's not glitchy, which we don't know yet.
Yeah, that's a good point. Maybe one could construct like the same Betti table somehow of Licci and not Licci, which would upset my dream, for instance. Any
Okay,
other?
so are there any other question for Craig? Bernd, did you solve the problem, Craig?
No, unfortunately not. No. Needs a little bit more time.
We'll need a little more time for us to solve it.
Well, thank you very much for inviting me.
So Craig, I have a
Thank
question.
you
So
for
you
the talk.
said
It was
that,
great. It was a great talk.
thank you.
Yeah.
So you said that if you use non-homogeneous linkage, you can get, I mean, it gives you a different concept, or maybe you can get faster to a complete intersection.
I was just saying we don't really understand the relationship completely.
Okay.
For linkage in general, there are totally different equivalence relations, homogeneous or not homogeneous. But as far as linkage class of complete intersection is concerned, one doesn't know. It could be that they're actually equivalent. But just being Licci, homogeneous.
And is there a candidate, or
What do you mean?
A candidate to show they're different.
to show they're different?
No, there's no. I mean, the conjecture is they're equivalent.
That they're the same. Okay.
Outside the Licci case, they're easy counterexamples because there are these the Hartshorne-Rao modules, whether they are isomorphic homogeneously or non-homogeneously. Of course, that is a difference up to shifts and duals, of course. So you can easily manufacture counterexamples. But in the Macaulay case, in the perfect case, these obstructions vanish, and then of course one doesn't know anymore. If the two notions are equivalent or not.
All right, thank you. And by the way, Craig, can you save the notes and maybe email them to me so that we keep track? Post them on the website. Is that?
I'm happy to do that, but I don't know how to do it. So if you tell me how to do it, I'll be happy.
Okay.
Yeah, I will. Yeah.
Thank you.
But are these posted on the website eventually?
I think we're trying to.
Yeah, for those that we have, we do.
Oh, okay. Well, I will try to send them to you once I know how to make a PDF out of.
I'm going to stop recording now, by the way.
Oh, yeah.